Hello, let's talk about the physics of interface traps. And this is in the context of really understanding more about threshold shifts. And again, the threshold is when a MOS device turns from depletion into inversion, and that's when you have a large number of inverted carriers available under your gate for transport in a useful transistor action. Okay? And the voltage at which that occurs is, of course, critical to determine the operation of these transistors. Okay, so let's look at some interface traps. So here's a picture, an SEM of a transistor. You can sort of identify source, drain, and gate. So at the interface, you can see that you have a silicon channel that is crystalline, and then you have a gate oxide that is silicon dioxide. So for every silicon, you have two oxides that are connecting. And in a pictorial way, you can sketch this out in a form like this in one dimension, where you have a bunch of silicon that sits under here in the crystalline silicon. You have a terminated surface where you have dangling bonds, and those dangling bonds want to connect to some other atoms. And they can connect to the oxides that are in the silicon dioxide above, and there will be some other dangling bonds that might connect to a hydrogen. And we'll talk about how hydrogen might get into the system in a couple of minutes. So if you have a more three-dimensional view, you can see that this silicon dioxide sort of builds again a tetragonal type distribution. And here is a more detailed view as well. Okay? So there's local ordering of this structure in tetrahedra, but in a longer range order there is no such thing as a long range order. So in the nearest order, in the nearest connectivity, it's in a tetrahedral form. All right. So we've seen similar sketches when we looked at interface states before, many moons ago, I guess. And we talked about having dangling bonds in the system. We also said that these dangling bonds will be typically distributed throughout the gap. So you have states that are available, and their eigenvalues, if you will, are in the energy range of the gap. And when they're in the gap, then we have some issues, and we calculated a whole bunch of things in terms of Shockley-Reed-Hall recombination rates, etc. Right? So if you don't do anything to the structure and just count the number of states at the surface, you will have about 10 to the 14 per square centimeter of unpassivated bonds. Now that would correspond to a lot of charge that is being bound or not bound at the surface. Okay, so that would be compared to a doping of a volume that's 10 to the 16, 10 to the 17, you have a comparable charge. It's a no starter to build a device if you had surface states at that height, at that amplitude. So you have to do something to those surface states. So if you don't do anything, you're at about 10 to the 14. Now, if you have silicon dioxide on the top, you begin to passivate some of those bonds by having connections to oxygen. Okay, again, the silicon is in a tetrahedral form, surrounded by these oxygens, and so they will not bond or get close enough to the silicon. Okay, oxide is in that sense preventing the silicon to bond to its other silicons. So you will passivate some of the dangling bonds with oxide. Okay, so if you just do the oxidation and measure the density of interface traps, called DIT, density of interface traps, you can get down to sort of 10 to the 12, okay? And there's a distribution of those, again, alongside the direction of the gap. Okay, so it's not just a flat line, there is a distribution that looks kind of like this. Okay, so those are the distribution of traps as you just oxidize the surface. Now, if you find ways to anneal this surface, then you can reduce the density of interface traps down to 10 to the 10. And then that charge and trap density becomes technologically to a level where you can handle it and you will not have a malfunctioning device. That's the DIT you want. So when you go to conferences and people talk about new materials and integrating new processes, they talk about a DIT, and you want to hear 10 to the 10, 10 to the 11. If anything is bigger than that, you will see practical people roll their eyes and say, well, that's going to be a challenge to do something in real technology with that. Okay, so the surfaces have to be passivated. Okay, so how do you anneal such interface states? So if you oxidize at higher temperatures, okay, you have more atom motions, so to speak, and then the oxygens will have a better or more time, if you will, or explore in thermal vibration a phase space that is larger, and they eventually can find sort of the optimal connectivity to the underlying silicon. So you will passivate more bonds if you oxidize in dry conditions to a higher temperature. Okay, so 1200 Celsius is a typical oxidation temperature. Now, if you anneal the structure by also including nitrogen in the gaseous phase, you can reduce the overall processing temperature. So you can go down and to lower processing temperatures, down to 600 Celsius, and have the same passivated bonds. Okay, so this is data on a 111 surface, and here the value that is being achieved in this experiment is 2 times 10 to the 11. So it's already significantly lower than the 10 to the 14 we talked about. Okay, so the point is to lower it with just dry oxidation, you'd have to have high temperatures, but you can also include nitrogen and basically reduce the processing temperatures. And why would you want to reduce processing temperature? Well, if you have really small structures, then not only the oxygen here in the silicon dioxide moves around, but the overall structure underneath can move around as well. And if you have thinly grown layers, etc., you might do damage there by too high of a processing temperature. All right, so what you can also do is while you anneal, you can include hydrogen. And that's called a forming gas anneal. And there's multiple forms of introducing this hydrogen into the system. I'm not going to go into the details of that. The key element is hydrogen is the smallest atom we have around, right? It's one electron and one proton. And it can diffuse about through anything. And so if you expose the surface and the growth process to hydrogen, then the hydrogen can find the open bonds. Then there has been some work of a colleague of mine years ago, which considered different forms of hydrogen, heavier forms, deuterium, which then ultimately at the end binds the hydrogen atoms that have an extra proton more closely to the structure. It makes it a little bit bigger. I don't know exactly what the processes are, but I know that if you do it with deuterium, it could be shown that you have a better passivation. But frankly, I am not sure right now what processes are being used for this passivation in today's technology. I just would like you to know that you can introduce hydrogen to passivate the bonds and therefore reduce the traps further, the dangling bonds further. So as oxidized, we mentioned before, 10 to the 12. If you anneal it further, you can get down to 10 to the 10. And it's interesting that you see these curves of density of interface traps, and you see the distribution where it's low in the middle of the gap and it gets higher towards the edges. And if you remember when we discussed Shockley-Reed-Hall and the recombination rates through traps, we found that really critically important are the energy ranges that are within a Fermi level, either the true Fermi level or the mirror imaged Fermi level, and only the basically mid-gap trap states or towards the middle of the gap are relevant. Remember, we had discussed this windowing function over which we can integrate and the charges that increase the Shockley-Reed-Hall recombination rates. So really remember, so these charges in the middle are important. The ones that are on the edges here, they aren't relevant to the recombination generation. If you don't recall that, maybe go back to the lecture on the derivation of the Shockley-Reed-Hall. All right. The data shown here is 111 surface data, but 110 surfaces have 1/3 less dangling bonds. And if that sounds suspicious, I'll suggest you go back to the section on crystals and you go on NanoHub and rotate the crystals around and look at the bonds at certain interface cuts, and you'll see that the 110 surface has less bonds, less dangling bonds by 1/3. And that's why typically the semiconductors are processed on a wafer that is oriented upwards in 110, because as you grow on top an oxide, you have just a reduced number of dangling bonds, okay? So crystal orientation again shows up here rather relevantly. All right, so if you had a structure that, again, we have here an N-type substrate where we measure the CV. In a way, if you have not done any anneal, you'll get a CV curve here as in blue, and after the anneal, the curve looks sharper. So something happened between the before and after. Well, that's what the label says, but and we'll go into some more detail where that sharpening of the curve comes from. And if you remember, well, it's hard to tell on this scale at any rate. The CV curve, relatively speaking, is pretty sharp. If it's stretched out, there's something really wrong, and we'll explain what that means. Okay, so let's consider these different donor and acceptor traps in the gap. And let's define these as donor levels as first, okay? So these are traps that want to be donors, so they want to provide an electron. So once they provided an electron, they're positively charged when they're empty, and they're neutral when they're full, okay? And how are we determining whether they're neutral or empty? Well, we draw in a Fermi level for these traps, and at 0 Kelvin, it would be very easy. Anything above the Fermi level would be empty, and everything below the Fermi level would be full, because we're talking about electrons filling their states, okay? All right. Now, if we're talking about an acceptor level, it's kind of flipped. So an acceptor level is negatively charged when it's full. So it's a dopant that would like to accept an extra electron. So it turns from Na to Na minus, right? So it's negative when it's full, and it's neutral when it's empty. All right, so again, right, you draw in a Fermi level like this. At 0 Kelvin, it's easy again. Fermi level, speaking for electrons, means everything below the Fermi level. Electrons are occupying their states that are available. So there's acceptor states available here. They accept those electrons, so they're going to be negatively charged. And anything above the Fermi level would be empty. Obviously, at room temperature, that distribution is not as sharp. But if you look in terms of the overall extent of this gap, remember the gap here is, in silicon, is 0.1 eV. And kT plus or minus 2 or 3 kT, so plus minus 1 kT is 50 milli-electron volt. Okay, so the Fermi level on that length scale, or in energy here, on this energy scale, is pretty narrow. Okay, so even at room temperature, the distribution between empty and full is, or the transition is pretty narrow compared to the overall gap. Okay. Now, the interesting part here is that hydrogen passivation can act as either a donor or an acceptor. It depends on the detail of the bond configuration. Okay, so you can study those details theoretically through a variety of, say, density functional theory, etc. Or you can trust the experimentalists that I have measured this out to some vast degree of detail. So, and if you combine this when both are present, you can see that there is a distribution of this charge across the Fermi level, and it makes for an interesting balancing of charges and accounting for those charges. And we'll step through this slowly. So let's look at the donor-like interface states first, okay? And let's look at an N-type semiconductor. And now with the N-type semiconductor, that's equal and opposite to the P-type, if you will, the CV curve is again flipped. I mentioned this earlier in the sections. So your CV is flat for positive biases up here, and then it drops down as the parabolic distribution, and then it reaches threshold and roughly stays flat. Okay? So now if you have donor-like interface states and you have the Fermi level here, what did we say? Well, they are donors. They would like to give an electron, but if the Fermi level is above, then they haven't given away an electron, so they are full. Okay? So there's really no threshold shift in that case, and in this kind of bias condition right now. And so the two capacitance measurements lie on top of each other. You can assign some alpha of Vg, which is accounting for the bias dependence of the filling of these donor-like trap states, okay? And this turns it now into a nonlinear function, right? Because this alpha depends on Vg. And we'll look through some slightly different bias conditions in a second here. So in this condition here, when all the donors are full, so they're neutral, this alpha is 0. Now, all donors full, they're neutral. Now, let's consider the case where we're driving this towards depletion, okay? So we're pulling the potential here up in the metal, right? So we're beginning to have band bending up. But the way this looks right now, the Fermi level is still sort of in the middle of the gap, right? So we haven't quite hit inversion yet. We would do that when the Fermi level sort of hits the same, we're here, ballpark, right? But either way, the Fermi level is now roughly here mid-gap in this sketch. So in this sketch, all the electrons, all the donors, not all the donors are full anymore. Some donors are empty. The donors that are above the Fermi level are empty and they're positively charged. And then again, the donors that are underneath the Fermi level remain neutral. So in that case, this alpha coefficient is somewhere between 0 and 1. That is the correction of the trapped charges at the interface. If this distribution would not be voltage dependent, you would see a solid shift like this, right? So you just shift the curve over. But of course, it's not quite solid, and we'll get into that in a second. Now, if you apply a voltage that's then close to inversion, you've basically reached a point where this distance here between the valence and the conduction band is the same as what you had here in the flat band condition. Then all the donors are empty, they're all positively charged, and this value alpha as a gate voltage is now perfectly 1. Okay? And then you get a correspondingly solid shift. Okay? Now, as now stated multiple times, it's not a solid shift, but it depends on voltage, and it's sort of a smooth shift. At least in a pictogram form, you could draw in a green dashed line here that sort of indicates, as a function of gate voltage, there will be transitions between these continuous curves. And obviously, these are just for 3 steps as shown. Obviously, this is a smooth transition. And you kind of get a feeling for, oh, now I get why this curve here might overall stretch out like this, right? So that's the idea of this model. Okay, now let's look at the acceptor-like interface states. And let's start out with the condition in inversion. We start out from the other end. So we're down here. So we're in inversion, the Fermi level inversion, right? Remember, this is an N-type semiconductor, right? And so the majority carriers are N, and you have a bunch of holes piled up in here. And the Fermi level is close to the valence band, but it's inverted, okay? So in this condition, where the Fermi level is kind of almost under the gap, then all the acceptors are empty, and they're neutral, okay? So no shift at all. Now, as we go in voltage this way, we expose some acceptors, and only some of them are empty. And others are, make sure I have they accepted electrons, right? So the Fermi level is above them, so they accepted an electron, so they're negatively charged. And you will see this alpha needs to now have a value that's between 0 and 1, just like with the donor case, and you see a threshold shift into the other direction, okay? Because it's now negative charge on the interface, okay? Now, if we go all the way to the flat band condition, where we have no more inversion charge, and we have just the exposed donors in the depletion region. We have now the Fermi level close to the conduction band edge. The Fermi level is covering all these acceptor states down here. And so all the acceptors have accepted electrons. That's what confused me, right? They're full. They're full. Okay. No wonder I was confused. I presume you might be confused. Okay, so all acceptors have accepted an electron. It's now negatively charged. That's this -1 here. And this alpha term should become roughly 1. Again, the curve shifts all the further. It is, you can sort of symbolize it with sort of step-like behavior, but of course, overall, this will be somewhat of a smooth curve that will lie across here, okay? So you can put all of these together, the acceptor and donors combined, and you overall see a CV curve that's stretched out quite a bit, okay? So there's a donor-related stretch out, there's an acceptor-related stretch out, and of course, this is not just little step-like things, but it's really continuous. And that is how you get to the case where if you have bad interface states, characteristics in your device, and you haven't annealed, you have a CV curve that's stretched out like this, and after the anneal, it becomes more like a CV curve that you would expect in an ideal sense, where you don't have significant numbers of interface traps anymore. All right, so we talked about the physics of interface traps in the last segment here. We covered all of these corrections to the threshold voltage from the ideal case. We looked at metal contacts, that just sort of a solid shift being built in the difference between the work function in the metal and the work function in the semiconductor. We talked about charges inside the oxide. Based on some moment expression, we can calculate how much the threshold shift will there happen. We can have the same thing so these were for mobile charges, where the moment of the charge can move from throughout the oxide. There's a similar expression if you just had fixed charges. And then we talked about interface traps in the system, okay? So these non-ideal threshold characteristics are important because they can determine at what biases your device turns on. And they depend on the substrate work function, trap charges, and interface charges. And you might find cases where this might be not just always detrimental, but you might want to design some of these features into these threshold shifts, okay? So depending on what kind of threshold you'd like to have, you might design the metal work function to be quite different than the semiconductor work function. So that wraps up these non-idealities of the MOSFET and the threshold, and I'll see you in the next section. Thank you.